Hey, John, this is Dave, and I just wanted to work through that problem that you referenced in your email. Actually, there's three of them, so I'll make three separate videos here, and we'll share them out on YouTube, and make sure that you're clear on those. This type of problem is a problem that I think it pops up in section 9, where you're talking about kinetic energy of rotation comma moment of inertia, which is sounds very complex, but really it's not that difficult as long as we have the right equation. And all of this stuff is equation based. And if we were meeting together in person, you guys would be developing an equation sheet as we work through this thing. But let me share a screen and I'll walk through an example, and then we'll get into specifics of this particular problem. Okay, I think the section numbers are the same. This is the only access to this text that I have as a PDF that I can share with you guys. So it looks a little different than your text, but it says a revolving body possesses kinetic energy. Its magnitude depends upon the speed of rotation, the mass, and the shape of the body. Okay, and then we were given an equation for that. And let's see, where is that? Here's all the J numbers that we looked at. Of course, the J number is unique to the shape that you're working with. And luckily, those are all given to us, right? And we don't have to derive those, but those J numbers are given. And so our particular equation that we're looking at, it relates to kinetic energy of rotation. So it is this equation, number 8, where this is kinetic energy in joules, and the J is the moment of inertia. This is always given to us. We don't have to calculate that. This is not a physics class. This is the rotational speed, and this is a constant that is exactly equal to pi squared divided by 1800. And that's another number I'm glad we didn't have to derive. But as engineers, we're just going to take these equations, they're going to throw them over the wall, and then we're going to apply them, right? And so, that's the key. That's the type of problem that we're trying to work with these homework problems that you're given, that were given to you. So if we apply that equation, then we should be able to work through this pretty easily. Let me pause this and bring that homework problem up so we can see with this problem. I can't draw on these Word documents like I can PDF. I'll just try to highlight it. But this J number here is 5 kilogram meter squared. That really should be a multiplication in there, for the J number designation. It's asking for the energy, and that would be in joules. And then the rotational speed, that we're looking at here, we'll get that from these values that we're looking at here. Okay, so we'll work through each one of those independently based on that equation. Okay, so here's our first situation. What is the energy and going from 0 to 200? All right, so this is this number. I've already got these calculated out. The J number is 5. Okay, and if we put the units in here, we would see that, of course, they all work out for us. 200, it went from 0 to 200, so that squared. And if I multiply all that together, I should get 1,096 joules. Okay, and that is going from 0 to 200. Now the next one here, the next one says, let me go back. I got to go back and check this. Okay, and then so the next problem says to go from 200 to 400, right? To go from 200 to 400, what is the energy? And so what he does to solve this, and I had to go back and think about this for a second myself. Again, I've got this, right, times 10 to the third. The J number doesn't change. That is characteristic of the problem. And then so the value, and I guess we could use some more complicated math and get there uh, differently, but I think this makes more sense. And so I'm going to calculate it for 400 RPMs. And when I do that for 400, I get 4384 joules. Okay. And then, so therefore, the three dots, what was the energy needed to go from 200 to 400? Well, at 200, it was 1,096 that we figured out before. So this would be 4384 minus the 1,096, and that would give us 3288 joules. Okay. Again, just thinking through this, what does this say? Kinetic energy of rotation, so what is the amount of energy to go from 200 to 400? Well, we start at 200, so we're already at 1,096. We're already there. That energy was already input. So the next situation is going from 200 to 400, and so that is the 200, that the joules from 200 subtracted from the joules at 400. And then the last situation is kind of different. He says, I'm going from 3,000 to 400, so we're slowing it down, we're breaking it, in other words. So the kinetic energy, the best thing to do to work that is, did I say 4? It's 3,000. Yeah, I don't know if I said 4,000 or 3,000, but it is 3,000. So it's going to be, again, 5.48 times 10 to the minus 3, which is our constant that's given. J number is the same. We're going to plug this in for 3,000. And when we do that, we multiply this out. And let's see, at 3,000, it comes out to be 246,000 joules. Okay, that's for 3,000. And then what I'm doing is I'm bringing it down to 400. I don't need to calculate 400 again because I know that value is there. So what I'm going to do now is I'm going to take 246,000 joules. I'm going to subtract the 4384 joules from that. And what actually is happening here, the difference between those two is 242,216 joules. And that is not energy that I need to put into this equation, but that is the amount of energy that needs to be released, dissipated. Usually when we talk about flywheel, we're talking about, heat, energy dissipation. So before I could get to that situation, I would have to dissipate that much energy before it would slow down from 3,000 to 400. Okay. So let me know if you have any more questions about that. If you're not clear on where that's coming from, the equations used, why we used them, and that's not a straightforward problem. And always kind of laugh. I'm wishing more people would ask me questions because the only thing that indicates to me is that you're making the effort to try to work these out. Okay, now I'll make some more, two more on the other two questions that you had.